The last irreducibility criterion that we're going to go over, there's lots of irreducibility criterion out there. But the last one that we're going to go over is reduction modulo P. So I'm going to assume that everyone knows what congruence modulo n is. There is a homomorphism of rings from Z adjoin T to Z mod P adjoin T. If P is prime, well, this is true for any n, actually. Let me put an n here. For any n in n, called the reduction modulo n, where you take a polynomial and you reduce modulo n. So for example, if n is 2, this homomorphism might take the polynomial t to the 2025 plus 2t squared plus maybe minus 5t plus 10, and if I'm going to reduce modulo 2. So what is it going to do? All the odd coefficients are going to become 1, and all the even coefficients go away. So this is going to go to t to the 2025 plus t, because 2 and 10 are congruent to 0 mod 2. Okay, so this always exists. It's a homomorphism. It's not hard to show it's a homomorphism. It's quite easy. But it's a homomorphism. When P is prime, Z mod P is a field, and we use FP to really indicate that it's a field. All it is Z mod P, but we use F to really emphasize its field properties. And so FP adjoin T is a domain. In particular, we would want to reduce a polynomial mod 4 and analyze whether or not it factors, because Z mod 4, of course, has 0 divisors. You have 2 times 2 is 0, and that causes issues with factoring. So we really want a domain when we look at factoring. All right, and let's notice something then. So if P doesn't divide the leading coefficient of F, then the degree of F stays the same, mod P. So for example, when n was 2 up here, 2 doesn't divide 1, of course, and so the degree stayed. It was 2025 in Z adjoin T, and it's 2025 in Z mod 2 adjoin T. So the degree stays the same. If P did divide the coefficient, so suppose I put a 2 here, what happens? Well, that's going to become a 0 now. The degree goes down. Okay. So if it doesn't divide, the degree stays the same. If it does, the degree will decrease. Okay. But in particular, we're going to look at the case where it doesn't divide. We want this to happen. So if f of t, well, I'm not going to write of t. If f factors is a factoring in Z adjoin T, then for any P that doesn't divide the order P not dividing leading coefficient of F, that P also does not divide the leading coefficients of G and H, because the product of those is the leading coefficient of F. We get a factoring of the reduction modulo P of this guy. And this is true for all primes not dividing, of course, the leading coefficient. You will always have that happening. So if you were reducible, you are therefore also reducible mod P for any prime not dividing leading coefficient. So what this tells us then is if there exists a prime, again not dividing the leading coefficient of F, such that the reduction modulo p of that prime, which I'll write as f bar, is reducible if this is irreducible, then f must be irreducible. All I've done is negate the previous guy. So if you could, if we look at the contrapositive, if f is reducible, then it should be, the reduction modulo p should also be reducible. If we take the contrapositive, we get this statement. All right, this is great. This is fantastic. So let's do an example of this. So example, let's consider the polynomial f of t is t to the fourth plus 15t cubed plus 7 over z. And what we're going to do is we're going to simplify this a touch. We're going to reduce modulo 5. Why 5? Well, it doesn't work if you do modulo 2 and 3, as we'll see. So we're going to do it correctly, and then we're going to see what happens if you picked a wrong prime. So reduce modulo 5, then f bar is going to be t to the fourth, the 15 goes away, and 7 mod 5 is 2. Okay, so that's what we're going to look at, and we're going to look at this in f5. All right, so let's start by ruling out linear factors. So the claim is that f bar is irreducible here. And so how could it factor? Well, it can have linear factors. Linear factors correspond to zeros. Now we see some utility here. The zeros are just elements in the number system we're using. We're using f5. So there's 5 possible choices. Well, f bar of 0 is 2, which is not 0. F bar of 1 is 3, which is not 0. F bar of 2 is 2 to the fourth. Well, anything to the p minus 1 in fp is just that thing back. In particular, you'll find 2 to the fourth is 2. Is 1, my bad. Anything to the p is that thing back, so p minus 1 is 1, sorry. So that's 1 plus 2, that's 3, that's not 0 in f5. And then what do we have? We have 3, which is actually negative 2 in f5. And t to the fourth, that's an even power, it doesn't see negative signs, so we get the same answer as the 2 case. And then similarly, f bar of 4, well, that's f bar of negative 1, because we're in f5, and this doesn't see negative signs. So we get the same answer as 1. So in none of the 5 choices for zeros do we get a 0, so there's no linear factors. And then what do we have to do? We have to rule out quadratic factors. So suppose it factors as a product of quadratic terms. We can assume the polynomials involved are monic, so have leading coefficient 1. And if we multiply this out, I will ask you this sort of problem as exam problems, so make sure you can do these sort of simple arguments. The possible cubic terms are a, and then I think plus c. And then the quadratic, we're going to get an AC, and then a b and a d. So AC plus b plus d. And then a linear guy, we're going to get an AD plus BC, and then we're going to get a BD. All right, so what does this tell us? Well, there's no cubic guys in t to the fourth plus 2, so a plus c needs to be 0. There's no quadratic guys, so AC plus b plus d needs to be 0. There's no linear ones, so AD plus BC needs to be 0. And then the constant term is 2, so BD needs to be 2. All right, so let's see. Let's go ahead and observe that the first equation we can write as A is negative C. And then we can plug that in, I think, I don't want to plug it into the second equation yet. we'll plug a equals negative c into the third equation. And I think I'm going to write this as c is negative a, sorry. So we'll plug in c equals negative a, and we're going to get AD minus AC is 0, or AB is 0, rather. And actually, let's go ahead and factor out the a from that. So a times d minus b is 0. And BD is equal to 2. So a times d minus b is 0. Since we're in a field, remember this is an instance where prime is important. Since we're in a field, we have cancellation. Well, we just need a domain for that, but we have a field, which is a domain. So this tells us that a is 0 or d equals b. But in the first situation, c also has to be 0. And if we look at the, therefore, if we look at the second equation, a and c are both 0 there. So b is negative d. B cannot be equal to both d and negative d, because that would mean they're both 0, but they have to multiply to 2. So this is a contradiction. Where's my blue lightning bolt? Here it is. As BD is 2. Okay, so it cannot be that A is 0. We can X that out. We've ruled that out. Oh shoot, hang on. I got ahead of myself. Dang it, 1 second here. Let's see, I guess I'm using B is D here. Let me back up for a second. Can't use that because we're not in that case yet. We will use that argument when we get to that case though. So B is negative D. So B is negative D. This says that, I think this says that B squared is negative 2, this equation here. Okay, B squared is negative 2. You can quickly check in F5 that B squared is negative 2 has no solutions. 0 squared is 1. 1 is not, this is of course 3. 1 is not 3. 2 squared is 4. 4 is not 3, and you just keep going. Okay. So this cannot happen. So it must be that B is D. So if B is D, well, then instead of having B squared is negative 2, B is D, so we're again going to use this last line. This would tell us then that B squared is positive 2. Again, that cannot happen. All of the squares in F5 are either 1 or 4. So you can't have either 2 or 3. So this has no solution. Okay, so I guess I didn't actually need this second guy here. All right, so therefore this guy can't happen. And therefore there's no solutions. Thus there's no possible factoring. And I'm going to go in real quick, and I'm just going to highlight in yellow all the parts where we use the fact that we were in F5. So that was in F5. This was in F5. This was technically being in a field or in a domain. So let me highlight that because F5 that did technically use some property of F5. And then here, all of this, checking that this there was no linear factors. We only had to check 5 possible roots instead of however many there are. So by reducing modulo 5, we were able to simplify some of the work. Now you could do this but with your hands, in Z as well, but this is the reduction modulo 5 technique. Let me also notice you could have picked a bad prime. You could have picked P is 2. And if you reduce F modulo 2, F bar becomes T to the 4th rather, plus 1. Plus, sorry, T cubed, plus 1. All right, so you again would check for linear factors. So you look at linear factors, and these are roots. And we're, of course, working in F2. And you plug in 0, you get 1, and you plug in 1, since we're in F2, you also get 1. Great. And then you might say, well, let's look for quadratic factors now, because you have to rule out all possible types of factors, not just roots. So you say t to the fourth plus t cubed plus 1 is t squared plus at plus b times t squared plus ct plus d. And you're going to get a similar set of equations. You're still going to get, well, actually mod 5, we're going to get some slightly different things. Let me multiply this out real quick. So I think we found something like t to the fourth plus a plus ct cubed from before plus ac plus b plus dt squared. You're going to do this multiplication lots of times. So, there's no harm in doing it more. And so then we get a system of equations. We get a plus c is 1 now instead of 0. We still get ac plus b plus d is 0. And we still get AD plus BC is 0. And then we get BD is 1. Well, we're in F2, right? So if B times D is 1, the only possible choice for numbers we have are 0 and 1. So this guy automatically tells us B is D is 1. So let's go ahead and plug it in, because neither of them can be 0, so the only other option is 1. So I'm just going to plug in 1 everywhere. If we add B and D in the second equation, 1 plus 1 is 2. In F2, 2 is 0. So this is just A times C is 0. And then this is A plus C is 0. And this last one doesn't exist. All right. It seems like we have a contradiction here, right? So I think what this says is that A and C have to be either both 0 or both 1, and this says they have to be opposite. So here we have a contradiction because these two equations are in opposites with each other. So actually, we could have worked in F2 instead of Z5, and our work would have been a lot easier. So we can deduce no quadratic factors in F2, and so it's irreducible because we've ruled out both of them. All right, so that didn't work out how I was intending it to work out, but nevertheless, that's another proof of the same fact. Let's try the same problem, but let's do it modulo 3 now. One of these is going to fail. So if we reduce modulo 3, f bar you'll find becomes, it was t to the 14th, and then we're going to reduce the coefficients mod 3. So I think mod 3, this becomes t to the 14th plus 1. All right, so I believe in F3, this should factor as t squared. I'm going to cheat a little bit here and look at the book. This factors as t squared plus t plus 2 and t squared plus 2t plus 2. So let's just check that real quick because I cheated a little bit. So we'll get t to the 4th, and then let's see, for our cubic terms, we're going to get 2t cubed plus t squared. So that's 2 plus 1. For our quadratic terms, we're going to get 2 plus 2 plus 2 plus 2. And then for our linear terms, we're going to get 2t plus 4t, so 2 plus 4. And then for our constant term, it's going to be 2 times 2 is 4. All right, 2 plus 1 is 3, mod 3 is 0. 2 plus 2 is 6, mod 3 is 0. 2 plus 4 is 6, mod 3 is 0. 4 mod 3 is 1. We do, in fact, get t to the 4th plus 1. Okay, so if we were to reduce modulo 3, we would get that it factors, in which case we'd have to try another prime. Or maybe we can somehow use this to show that the original polynomial was reducible. It's not. We showed it's irreducible over 2 separate primes, so we won there. If we were to guess wrong at the start, we wouldn't be able to conclude anything here. So let me just point out here, just the last thing I'll say. Sorry, this is another long video. The reduction modulo P, modulo 3 test in this case is inconclusive. We don't know at this point.